Okay, it's Berkeley time, so we can get started. Okay, so I want to start off. Hey. Over here. Okay, good. So I want to start off with talking a little bit more about lasso. I know that I think the last bit of lecture went a little fast for some people last class, so I'm going to redo that derivation for the scalar case. And then we're going to move to talking about a specific method, an algorithmic method that is often used for finding solutions to lasso. And then move to talking about Newton's method, which is a second algorithmic method that is, I guess it's a second order method, and we'll talk, you'll see when we come to it, okay? But in talking about lasso, so remember last time we were talking about the lasso problem, and here the point is that we're thinking about L1 regularization. So I'm thinking about the problem min over x, ax minus b norm squared plus lambda times, now I'm regularizing the one norm of x instead of in the case for a ridge where I have the two norm of x. And last time at the end of class, we were looking at the scalar version of this. Right, which is minimize so instead of thinking about this as a vector, we're thinking about just the scalar version of here, these squares. I guess I'll put a half here so it'll make my algebra easier. And now we're regularizing with the one norm of a scalar, which is just the absolute value. Everyone remember that we talked about this problem last time? Okay, good. And what is this problem? Basically, this part of the problem is what? What does it represent in the one-dimensional case? This is just finding the slope of a line, right? I have points a1, b1, a2, b2, a3, b3, an, bn, and I want to find the slope of the line that best fits all of them, right? That's what this minimization problem is. It's a standard least squares problem. But now we're considering it regularized with the L1 norm. And what was the approach we took to solving this problem last time? At this point in the semester, I recognize your faces. I know you were all in lecture last week, or last class, so. What approach did we take? You were all here, really. Yeah. Yeah. Basically say, observe that, okay, this is a convex problem, right? So one way to deal with this is by setting the gradient to be equal to 0, right? And what do we know in general for optimization problems? Well, when you want to optimize when you want to solve a problem, you look at all of the critical points. So you look at all the points where the gradient is 0, or the points that are on a boundary, or the points where the gradient does not exist, right? These are your candidates for the optimum point of a convex problem. So let's look at now the gradient of this thing. So if I consider d by dx of this, let me call this whole thing, let's say I call this whole thing f of x, then d by dx of f of x. Well, this is just equal to, this is really easy. The 2's just cancel. And then I have ai squared x minus ai bi. This is calculus you've all done many, many times before this class. And what about the gradient of this guy? What is the gradient of this guy? Does it always exist? No. Where does it not exist? 0. What is absolute value of x equal to if x is positive? X. So what is the gradient of this when x is positive? 1. So this whole thing is just lambda in the case where x is 0, greater than 0. Does the gradient of this change depending on whether x is positive or negative? Nope. So this is the same thing. Except now what do I write here? If x is less than 0, what is the gradient of this thing? Shout it out, shout it out. Negative 1 or negative lambda, right? Because absolute value of x is negative x when x is negative. Okay? And what's the case that's remaining? Where does the derivative not exist? X is equal to 0. Does not exist when x is equal to 0. Okay? Everyone see this? Everyone understand this? We're good? Okay. So what did we do from this point on? How do we proceed to try and understand from this what the optimum is, right? What do we want to find here? What is the thing that we're trying to find?
Critical point.
Critical point, but more like concretely. Are we trying to find A or B? No, we're trying to find x, right? That's clear to everyone, right? What we're trying to find is x. But what are our cases based on? Our cases are also based on x. Okay? So we're trying to find x, and we also have cases based on x. So do you see that there's an element of a chicken and egg problem here? If I knew x, I would know the derivative. But I don't know x. I'm taking the derivative to find x. Okay? So how do we go about resolving this chicken and egg problem? Okay? Does everyone see that that's what we need to try and do? Yes? No? Head nods? Something? Okay, good. So what we do is we make assumptions, right? We assume, let's say, that we have the case 1. Let's say x was greater than 0, right? Let's say somehow we knew that x was greater than 0, okay? If we knew that x was greater than 0, what would x have to be equal to, the optimum x? The one that satisfies which of that? The top case, right? Yeah? So I'm going to say if x was greater than 0, I know that my optimum point is the point where the gradient is 0. And so I'm going to set that gradient equal to 0. So what do I get? I get sigma ai squared times x minus sigma ai bi plus lambda equal to 0, right? This is the case that I get. And so from this, what is x equal to? X is equal to the sum of ai bi minus lambda divided by sum of ai squared. Okay? Nothing fancy here. I just did some algebra. But what is the interesting or fancy thing that I do have to do now? What did I assume to make this calculation valid? That x is greater than 0, right? And now I have received a value for x. How do I ensure that what I have done is still valid? I have to check that this whole thing is actually positive, right? I have to check that my assumption was valid, right? So this is positive only when is strictly greater than lambda. Okay? Right? Clear to everyone? Why does the denominator not matter? Sum of square of real numbers is always positive, right? Or non-negative. So we're good here. Okay? Good. So now how do I proceed from here on out? What's case 2? Case 2, why, are you kind of not engaged because this is obvious and we already did this? Or are you not engaged because you're confused? I can't tell. How many people are like, this is obvious, we already did this, let's move on to the next part of the class? Okay, good. How many people want me to go through this? Okay, then engage or ask me questions. Otherwise, I'm going to skip and follow the people who want to skip forward. So what's the next case that we're going to talk about? X less than 0. What happens in this case? I can do the exact same algebra, right? And I can get that x is equal to minus sigma ai bi. Oh, sorry, not sigma ai bi plus lambda divided by sigma ai squared. Right? And now what do I need this to be? Do I need this to be positive or negative to verify my case? Negative. Okay. So this implies that this is only true sigma ai bi is less than minus lambda. Okay? So what I want you to now think about is, first, what happens when lambda is equal to 0? What happens when lambda is equal to 0? Is there any regularizer? No, right? So the solution should just be the least squares solution. If lambda is equal to 0, what is x equal to? This whole thing is differentiable. This is just the least squares problem. You should have this memorized in your sleep. If lambda is equal to 0, x is just sum ai bi divided by ai squared, right? Remember, what is the formula for least squares? Here, a is just a vector because we're in the scalar case. So this is exactly what you get, right? Does this match with what we're getting here?
Yeah.
Right? So lambda equal to 0 gives you the exact same thing. So that's observation number 1. So you can start looking at this lasso solution as a perturbation, as a change on the standard least squares solution. Right? Does everyone see that? Okay. Good. So we have this. Now I want to try and look at this and interpret this graphically. So here I'm thinking of this axis. And this axis is the value of sigma ai bi. This is my x-axis for this plot. And kind of on the y-axis, I'm plotting the unknown x. Okay? So when lambda is equal to 0, when all I have is my x is this quantity, right? What kind of function of sigma ai bi is this? This is just a linear function of sigma ai bi, right? Right? If you think of this whole thing as equal to some quantity, how is x related to this quantity? It's just directly proportional, right? And the constant of proportionality is given by this thing. 1 over ai, sum of ai squared. Everyone see that? Yes? Give me some thumbs up. Okay, so if I was to draw this plot, remember this is not x and y. This what is nominally the x-axis is the sum of ai bi, and the y-axis is our variable x, right? So don't get confused by what the axes are. But this basically is something that looks like this, right? Going through the origin, and it's just a linear function. Right? You just take this number, scale it by 1 over sigma ai, and that will give you the value of the unknown. Right? That's what that function is. Yes?
Oh, wait, sorry, but isn't the sum of, like, the scaling factor is related to that, right? Like,
it's not just a constant?
You can think of it as just a constant because in this case, it's not going to matter. Just if you just plotted this, it's still just a number. You can think of them as two separate numbers. It's not going to be a problem.
But like changing one changes the other.
Not. Changing one will change the other, but think of them as just two numbers, and like that's still a valid interpretation of this thing. Okay. So now I want you to think about this for these two cases. Okay. So now we have solutions in two cases, right? We have solutions in the case where sigma ai bi is greater than lambda. And we have this case where sigma ai bi is less than minus lambda. So on this axis, what are the 2 points of interest? I have lambda, and I have minus lambda here, right? And so the regime when x is positive is the regime, which regime is that? It's the regime where sigma ai bi is greater than lambda, right? And so what is that equal to? Well, it's also a linear function just offset by this lambda, right? So instead of passing through 0, now it's going to pass through lambda. And so what you're going to get is something that looks like this. Okay, that's what your x is going to look like. It's exactly the same thing, just offset by lambda, and the same thing on the negative side. Okay? So what you're doing by adding this regularizer is you're saying, I'm going to take the least square solution and perturb it so that I start my function at lambda and minus lambda instead. Okay? And what is going to happen in this entire middle regime where sum of ai bi is between minus lambda and lambda? In that case, okay? In this case, can x be positive? No. Can x be negative? No. So what is the only value possible for x? 0, right? And so here, this is the point where the gradient of our function does not exist, which is always a candidate for our optimum point, or our optimum value. And so you have x is equal to 0 in this interim regime. What this is saying is that what lasso is trying to do is that the bigger lambda is, the larger the interval where x is being set to 0, right? So you can see that compared to the least square solution, you're more likely to set something to 0. Does that make sense? Why is x 0 in this interval? If ai bi is in this interval, you cannot be in this case, nor can you be in this case. Therefore, the only option that remains is that x is going to be equal to 0. Okay? So this is basically what I want you to understand, because it's the core of how then you solve. This is exactly how you go on to solve, and we'll see coordinate by coordinate any vector lasso problem. Okay? And this is why we talk about lasso as being as getting to sparse solutions. So now I want to show you this thing as a demo, because you could say that either x is greater than 0 or it's less than 0. But if you're failing the conditions for both of those, and x is going to be a real value, then the only option left is x equal to 0.
Because it's only when. It's not, so it's, okay, it's both directions.
Yes. Yes? Why does the larger reason make it more likely? So basically, just because the wider this is, the more fraction of the real number line are you setting the value to 0. Like, it's just bigger, that's all. Yeah. Okay, so what I'm going to do here now is something that you have all done many times before, right? How many times have you done polynomial fitting? Many, many times, right? You know basically that if I give you a bunch of data points, everyone can see this, right? If I give you a bunch of data points, these are some noisy data points, I can run least squares and I can fit this thing, right? And if you remember at the beginning of the semester, when we talked about ridge regression, we saw how if you had a bad condition number and you had poorly conditioned data, right? For example, I looked at this polynomial, but I looked at it in the limit kind of, if I, I'm looking at this range from like kind of -1 to 3 is my x values. But let's say I evaluated this polynomial at 100 to 103, right? Something like that. Then what is this polynomial going to look like? It's going to look very much like a straight line, right, in that particular interval. And so remember that demo where we couldn't, the condition number of the matrix was high, and it was doing a terrible job at fitting the polynomial? Remember that we did that? And then we said, let's use ridge as a regularizer. And we gave it the side information that, oh, remember, keep the norm of x small. Remember we did that? And then it suddenly started doing a much better job, right? It found reasonable coefficients for the polynomial. Jogging your memory? OK, good. So here, let's think about this. There, in that entire experiment, we assumed that we knew the degree of the polynomial, right? Whenever we're doing a least squares fit for any kind of polynomial fitting, we say, OK, I know this is a cubic polynomial. Let me try and find what the best cubic fit for this is, or best whatever, quartic fit. Whatever it is, I choose the degree of the polynomial first. Then I do the fitting. But in general, will I always know what the degree of the polynomial is? I might not, right? So something like lasso can come in very handy when you have to pick out a small number of coefficients from a very large number of coefficients, right? So for example, let's think about this. So here I have my true polynomial is this, 4x cubed minus 11x squared plus 7x plus 1, right? I'm doing ridge regression first, OK? And let's say I set my regularization parameter lambda equal to 1, just for something. And I don't know what degree polynomial I actually have. All I know is all I have is my noisy data points. So I say, well, let me guess. Maybe it's a 30-degree polynomial, right? Cubic polynomials are definitely a subset of 30-degree polynomials, right? I just have to set coefficients from 27 to 30, or sorry, 1 to 27 all equal to 0, right? And just have I have four things that I can that are not 0. Everything else is 0. So, okay. But when I try to do this, when I try to recover a 30-degree polynomial, what am I getting? I'm not getting particularly great values at all, right? Some of these high-order coefficients are indeed being set to 0, but I'm not doing a particularly great job at estimating my polynomial. Like, I'm doing something reasonable, but it's not the best thing. I'm not recovering my coefficients particularly well. Does everyone see that? Because I don't know exactly what my polynomial is, or my degree of my polynomial. If I was to instead set this to be 3, I do really well, right, when I know my degree of my polynomial. Look at the coefficients that are coming out, right? This is the W3 is almost exactly what it is. W2 is almost exact. W1 is almost exact, right? Do you see how good this estimation is? When I know the degree of my polynomial, versus if I don't. This is far worse, right? Like it's getting things way off. It's putting high weights on the 4th degree, 5th degree, 6th degree, so on and so forth. Okay. So now, what is the power of lasso? What did we talk about? What did we say? Lasso likes setting things to 0, right? Lasso finds sparse solutions because it likes setting things to 0. So intuitively, maybe lasso can help, right? Because we want to be setting things to 0. I want to recover. I know that there's only 3 of these coefficients or 4 of these coefficients that matter. I have 30 choices. Can lasso recover the right ones? And so here I just have an implementation of lasso. And now let's just see. Maybe I start with my regularization parameter lambda equal to 1. Takes a little bit of time to run. So you notice now lasso is taking longer to run than the ridge did. Why? Ridge, we have an explicit formula, right? Lasso, we don't quite have an explicit formula. We have this explicit formula in the scalar case, but we don't have an explicit formula in the vector case, right? So we're going to talk about how to compute a lasso solution in just a minute. But did you notice that it took longer to run? You can, in fact, see what it did. But now, when I look at this, oh, wow. Like, it puts some weight on the 4th degree. But this is already, like, this is, 3.1 is not that different from 4. My quadratic term is negative 12, but in reality, it's negative 11. It, like, is doing quite a bit better, right? And all of these, so many more of these are being set very, very close to 0. Do you see that? So now if I increase my weight on lambda, increasing weight on lambda saying, no, be more aggressive at setting to 0, right? So if I was to increase my weight on lambda, what would I get? Okay, now I'm being very aggressive. I'm kind of maybe even not getting quite where I want to get. If I was to set maybe lambda equal to 5, now I'm starting to get pretty good, right? Like I'm getting pretty good recovery here, setting most of these things to 0. So you have to, of course, play around with the exact value of lambda. This is a hyperparameter tuning that you have. You never know a priori what the right value of lambda is. But you can see immediately off the bat that this is doing much better than ridge at recovering a sparse solution. Does everyone see that? Yes? So do you see where something like lasso might come in handy as compared to something like ridge? Like each one has a different use case, right? And again, what we're trying to do in this class is give you the different tools and tell you how and when to use each of these different tools. Okay? So this is something you will set algorithmically. You'll set a tolerance. And you can basically set a tolerance at which you stop iterating. And depending on how much compute you have and how much time you want to spend. Well, if you don't know the actual degree of the polynomial, you say like, hey, I don't know what the degree of the polynomial is. It's probably less than 30. Let me guess 30, right? And then all subsets of polynomials that are less than 30 are kind of things that are fair game and in play, right? Maybe your guess of 30 is terrible. Maybe it's reasonable. You don't know. There's always some amount of like hyperparameter tuning, guesswork that is involved in learning problems, especially if you're trying to do something where you're recovering underlying structure without side information or without supervision. So there's definitely that aspect. So you would use lasso when you know you want your solution to be sparse. You would never use lasso if you don't know anything about the sparsity of your solution. Look at this picture. If lambda is larger, what is the range in which you're setting to 0? It's larger, right? So larger lambda means more aggressive. So the L1 norm, right? The L1 norm, what is the L1 norm? The L1 norm is just the sum of the entries of the vector, right? And it's the sum of the absolute values in particular. So fewer entries in the vector means basically smaller L1 norm, right? So when you're regularizing, when you look at this term here, this regularization term, so ridge says make the 2 norm small, right? This is saying make the 1 norm small. If you wanted to really just say that I want to set exactly to 0, the explicit way to do that is look at the L0 norm, right? But the L0 norm has challenges. It's not convex, so you don't want to be like it's really like a fictitious norm that we've kind of created, right? Because that's just counting the cardinality. But so a common relaxation when you have a cardinality constraint on the number of non-zero entries in your vector is to think instead about the L1 norm. And it turns out that we can actually rigorously prove that even looking at the L1 norm as a regularizer sets things to 0. Okay, so so the question is, if lasso tends to send things to 0, why do you have some things that are not 0, right? Well, because what we're saying is that if you're between minus lambda to lambda, you're going to end up 0 if your sigma ai is between this range. But it might not be in this range, right? And so for the cases that it's not in those range, you're going to have these values here. Okay, so if we wanted to force the vector to be 0, we could just say x is 0 and we're done, right? We don't do anything. But that's not what we want. We want to have something where some entries are non-zero and some entries are 0. We're not interested in the all zeros case. Make sense? Okay, great. Loss function. Oh, my loss function. My loss function is exactly this thing. Right? This is the loss that I'm training on. Oh, how do you do polynomial fitting, you mean? Polynomial fitting we've talked about many times. I'm going to defer that question, and we'll talk about it in office hours. Yeah. Okay. Great. Talk to me later if how to do polynomial fitting is not clear. Okay. I'm going to move on because there's other things that I want to get to. How much time do I have? I've always used more time than I want to. Okay. Good. Good. This is done. So what I want to introduce to you now is another descent method. And if you were looking at the notebook closely, you might have seen this name show up in the notebook, right? Coordinate descent is a common strategy that is used to solve the lasso problem, okay? What is coordinate descent? Well, let's consider the following setup. If I have some function f, let's say it's going from Rn to Rn, okay? And let's say f is convex and differentiable. I want to now find some x star. I want to minimize f of x, right? Let's say I found you somehow by magic an x star such that kind of this is true. Okay? So I'm saying, look at your function coordinate by coordinate. And x star is such that it minimizes your function along the first coordinate. Okay? So that means you've kind of fixed everything else and you find the minimizing point along the first coordinate. You find a point such that the partial derivative of f of x with respect to x1 is 0, okay? But you do this for every single coordinate, right? I find a point where partial derivative x2 is 0, partial derivative x3 is 0. If I just minimize my function coordinate by coordinate, does that mean I've found a global minimum? How could I know if I have a differentiable and convex function? So how would I know if I had a global minimum? I would look at the gradient of f of x, right? If the gradient of f of x was 0, I could say I had a global minimum, right? But now if every single entry of my gradient is 0, by saying that I'm minimizing in a particular coordinate, I'm saying that this is 0. What are the entries of this? Well, the first entry is partial with respect to x1, second entry is partial with respect to x2, so on and so forth. So this implies actually that the gradient of f of x is 0, right? And therefore, x star is actually a minimizer for the whole function, right? Even though I started out by thinking, oh, it's a minimizer in the first coordinate and the second coordinate and so on and so forth.
Gradient?
Sorry, IR into R.
Oh, okay. Okay, sorry.
Yeah, thanks. Okay? So this is the key idea that motivates the idea of coordinate descent. And the coordinate descent algorithm is kind of simple. Okay? Basically, it says, let's say you have some x. How do I want to think about this? Let's call x equal to, let's call the components of x, x1, x2, all the way up to xn, okay? And let's call some initial point. I'm going to call this x of 0. I'm going to kind of have a superscript here, okay, to denote my iteration. So this is my initial point. Okay? This is where I start out at. And then what I'm going to do is I'm going to do a minimization coordinate by coordinate. Okay? So I'm going to write x1 at my kth iteration is the argmin over x1 f of x1 x2 k minus 1, x3 k minus 1, all the way up to xn k minus 1. So what does this mean? I'm going to take my function. My function is typically is a function of a vector, right? But instead of minimizing over all of x, x has n elements. It's an n-length vector. I'm going to say minimize only over the first coordinate, okay? And fix all of the other coordinates. So I have some initial point, right? And I say, okay, fix x2 to xn, and now search for whatever first entry minimizes this function, right? So you have a function of n variables, and you turn it into a function of one variable, right? You turn it into a scalar problem, okay, which is easier to solve than the general vector problem, okay? So I have argmin over x1 of this thing. This gives me, and so this is basically I take everything at the k minus 1th time to give me the next thing at the kth time, okay? Once I do this, then I say, okay, now I have x1, I have my new x1. If I find x2 of k, I'm going to say I'm going to take argmin over now x2 of f. I substitute my newly found value of x1, take x1 to the k, I optimize over x2. x3 I have not yet found a new value for, right? So x3 is still my k minus 1th iteration guy. Okay? And I do this one by one by one sequentially. Does that make sense to everyone, what we're doing? So every time, instead of solving a vector, setting a vector gradient to 0, we're doing this by just taking a scalar problem. Okay? If I keep doing this, and I converge to something that is coordinate my coordinate, now minimizing where I want to be, right? I'm saying, let's look at f basically in one particular direction, right? By looking at one coordinate, I'm basically looking at the projection of f in that one particular direction. And so one by one by one by one, you keep doing this, turns out, we're not going to prove it here, but this will converge to your optimum point. Okay? This is called the method of coordinate descent. Of course, there's a condition. For coordinate descent to work, of course, it will work if it's convex and differentiable, but I actually want to apply it to lasso. Lasso is convex, but is it differentiable? No. Turns out this method can also apply in the case where your non-differentiable part is what is called separable, in the sense that it works, it can be separated into coordinate elements. So if I have f of x of the form g of x plus sigma h of xi, okay, where g is convex and differentiable, and h is convex. It need not be differentiable. Okay? So what does it mean to be separable like this? So for example, if I take the one norm, right? The one norm of a vector x, well, it's the absolute value of the first entry plus absolute value of the second entry plus absolute value of the last entry, right? So this is separable in the sense that I can separate it out into n functions, each function of which depends only on one coordinate, right? So here, each of the h's is just the absolute value of that xi. Does everyone see? So coordinate descent can apply, and you can prove convergence of coordinate descent, of course, if f is convex and differentiable, but also for f's that are of the following form, where you have a convex part and a that is also differentiable, and a separable part that need not be differentiable. Okay? We're not going to do any of these proofs here, but I want you to understand this condition. Okay? Does everyone see the basically iterative perspective of how we're going to do this? Okay, good. So now what I want to do is I want to apply this to the lasso. So here now my f of x okay? So now I want to find basically what is my gradient of my x. Or let's just say maybe I want to find let me remind you all, if I was to just write gradient with respect to x of 1/2 ax minus b. Okay, so I'm going to get a sip of water. In the meanwhile, just some reminders that you've also learned vector calculus. Do this out, and then do this out. This is kind of following the same pattern that we used for the scalar case. I'm going to drink some water. Okay, so that was my timer, and there's a question. Why would you ever want to use a coordinate descent method when we know that lasso can be expressed as a convex QP, right? So it's entirely possible that you will want to sometimes solve this as a convex QP. But the solvers for convex QPs are general solvers, right? And so they will treat this as a general quadratic program. If you can exploit the structure of the problem, you can sometimes get a faster implementation because you're using special properties of the problem, right? And so for lasso, it turns out that you'll see that using coordinate descent can actually make some of your computations a lot easier than they might be in the case of a general quadratic program. Okay, so let's look through this. So, okay, this is an exercise. What is this gradient? We've done this many times before. Right? Okay, good. So now if I want to find the partial of this entire thing with respect to that, well, I want to find basically the ith component of that vector, right? What is the ith component of that vector? I can consider this as, let's say, AI transpose AX minus B, where this is the ith row of A transpose, right? And that's going to give me the ith component of that vector. Everyone see that? And now what else do I have to do to get the partial of f of x with respect to xi? What else is remaining? So I've taken care of this term. What remains? This term remains, right? So when I take the partial of this, what is this? This is absolute value of x1 plus absolute value of x2 plus absolute value of x3, so on and so forth. So what is the partial with respect to xi? So I have basically, there's lambda, and again I have these cases, right? Exactly the same way we did there. So if xi is greater than 0, I have one thing. Otherwise, I have this term the same, and I have a minus lambda if xi is less than 0. And I have does not exist if xi is equal to 0. Exactly like we did in the previous case, right? Because the partial derivative of x2 with respect to x1 is 0. Right? We did learn some vector calculus in this class. We're good? Okay, good. So now when you look at this thing, did I erase this thing? No, it's basically exactly this, right? What is the dimension of this thing? This is a scalar. This is a real number here. So I can basically now solve this coordinate, the coordinate-wise lasso problem, exactly the same way that I solved the scalar lasso problem, right? By doing this coordinate by coordinate, I've reduced the vector case to the exact same scalar case that we already discussed, right? We already know the solution to that. I don't need to solve this out again because the structure is exactly the same. So what coordinate descent allows you to do is that even if you have a vector problem, what you say is that, look, minimize the first coordinate, hold everything else constant. Great. Now freeze first and third to n. Minimize the second coordinate. Keep doing this over and over and over and over again until your thing converges, right? Related to the question that I got about tolerance and how close do you get to 0, you say, well, you set a tolerance, you set a number of iterations, and then you decide that you've converged, right? So does everyone see how basically coordinate descent allows you to generalize the solution from the scalar case to the vector case now? And to answer your question, this can be at times much, much faster than thinking about it as a general QP, which would not take advantage of any of these special structures, right? Why is this true? So I look at the gradient of this. What is the ith component of this, right? This is a matrix. This is a vector. So the output of this, a matrix times a vector, is basically I have now the this is just a vector, so I just want the ith component of this thing, right? Great question. So for coordinate descent in general, does the order in which you solve the coordinates matter? There are two common ways to do it. One is to cycle through sequentially. So I start with x1, then do x2, then do x3, then do x4. The other way to do it is to randomize. And different cases, you have different advantages of each. The standard implementations are often sequential. And I think the easier proof is also for the, actually, I take that back. I don't remember which proof is easier to do for conversions. I can look it up and tell you, but I've forgotten. Yes? Sorry, behind you first.
For the randomized approach, is it like with replacement, like do all of them need to be or?
The question is for the randomized approach, is it with replacement? In general, yes.
Is there like the first one of the derivative, like it's exactly the same as the summation value?
Yes. I mean, it's essentially the same form, right? Yeah. Yes?
Can we also use gradient descent to solve lasso?
Can we also use gradient descent to solve lasso? Great question. Of course, you could also use gradient descent to solve lasso. There's a small hiccup that is not differentiable.
But don't we have to deal with that here when the xi is equal to 0?
Well, we have a specific way of using that. When we have, it's like a special structure that we're using, right? So if you were to just do gradient descent, you're gonna, you'll get somewhere, and then suddenly you're gonna get to a point where the gradient doesn't exist, and then what do you do? Right? You could use it for some time, as long as you didn't hit a non-existing gradient point, but then you might hit that. Here, even if you hit a point, there's way forward, right? Because of the structured way that you're solving it. Yes?
Once you minimize for is that like a final x1?
Oh, the question is a good question. So just to make it clear, once I minimize this x1, is that the final x1? No, that is not the final x1. So the way this works is I do this. I do this many, many times, right? So I'm going to do x1, x2, x3, all the way to xn. And then I'm going to do it all over again. And I keep doing this until I converge. So this k is your iterate number, right? So just like in gradient descent, you have xk plus 1 in terms of xk, right? Here, you're doing this the same exact thing, except you're getting the new xk coordinate by coordinate instead of all at once. OK? So you're not done. You don't just do this once. This is not just n iterations. It's k times n iterations. OK? OK, good. Excellent. I'm actually on track. So lasso is one example of something that has these special properties, can be solved using coordinate descent, but it's also an example of a quadratic program, right? And in general, quadratic programs are pretty nice, right? Maybe linear programs are our absolute favorite, but if you had to pick a second favorite, you would probably pick quadratic programs, right? So the idea that I want to now move to thinking about is, can we use the fact that we like quadratic programs to help us solve other kinds of programs? And can this lead us to yet another algorithmic approach? Okay? So we're leaving the realm of lasso, we're leaving the realm of L1 regularization, like that ends here. But I now want to talk about what is called Newton's method, which is now a second order descent method. Okay? So gradient descent talks about how do I basically successively walk towards my minimum, right? I'm here somewhere at my function value. Take a step this way, take a step this way, take a step this way. That's what gradient descent tells me till I get closer and closer to my minimum. And this is one way of doing it. It depends on basically the first order statistics, right? It depends on the gradient of the function. What Newton's method is it's a different way of doing this. But now instead of using just the first order statistics, it's also, well, it's not really a statistic, but the first order properties, it's using second order. So it's going to use the Hessian. And the key idea is that, let's say I have some function, right, that I'm trying to minimize. It's some function. If I could choose what function it was, wouldn't I rather have a quadratic? Everything is about wishful thinking, hopeful thinking, and laziness. Like, it's an underlying theme. Always you will see in engineering and mathematics. Why don't I pretend it's a quadratic? Okay? So I'm going to say, let's say I'm here. I'm at some point x naught. Instead of considering the function, let me consider a quadratic approximation to the function, right? Okay? So let me draw the best quadratic approximation to this function at the point that I'm at. Okay? So if this was a quadratic, then I could solve this QP, right? Now this is a QP. And then I can find the minimum of that function. Okay? Maybe this is the minimum of my actual function, right? Hope to get excited. So I go and evaluate my function. So this is my axis, so this is x0. And I find the point, I find the x-coordinate where my quadratic approximation is minimized. That gives me x1. And I say, OK, let me compute f of x1. Oh, it's not quite as small as I wanted. OK, let's pretend we're a quadratic again. Quadratic approximation. Let me find the minimum of this quadratic approximation. That gives me x2. Rinse and repeat until you have iterated long enough or you have converged to a minimum, right? This is the heart and the core of Newton's method. Pretend you're a quadratic. Keep solving quadratic minimization problems till you get to a minimum. Turns out, under certain technical conditions, you can prove that this actually works and will converge to the actual minimum. The proof is out of scope for this class. We're not going to do a full proof. But understanding how and why the method exactly works is fully in scope. Okay? So to be more precise about this, let's consider just some f of x. Let's say what I want to do now is I want to think about this f of x. Let's say I'm at x naught. And I want to think about f of x as a quadratic approximation. Or I want to think about a quadratic approximation to f of x. What is the tool that we have for thinking about a quadratic approximation? Taylor's theorem, right? So I can write f of x plus some v is equal to, well, f of x plus gradient of f of x transpose times v plus 1/2 v transpose. Now I get the Hessian. Okay? This is what I now have. Of course, if I want the quadratic approximation, I'm going to ignore these dot, dot, dot terms. And now I have this thing. Okay? So now this is a quadratic in what variable? V, right? V is the quadratic. V is the variable here. Okay? So now, is this a constrained quadratic or is it an unconstrained quadratic? Are there any equality constraints, any inequality constraints on this QP? Nothing, right? my f of x, my minimization of f of x was unconstrained. Like I'm trying to solve this problem. And instead I'm saying, let's locally consider right now I'm looking at this as a minimization over v. So this is the constant term, this is the linear term, this is the quadratic term, right? So when we talked about QPs a few lectures ago, right, there was one case that was kind of the easiest case. What was the easiest case that we had?
Unconstrained.
It was unconstrained. And in unconstrained cases, you can always explicitly write out the solution. And a bunch of cases you had that your minimum was going to be negative infinity, right? That was not that interesting. But there was the one interesting case where you had an explicit solution. And that was the case when this matrix here, when you had a convex quadratic, right? So H was positive, semi-definite, right? And we had a condition, remember, on the linear term. So let me write this out so that everyone remembers. If I had minimized right? Remember this case that we had? If H was invertible, right, and positive semi-definite, which means that it's positive definite, and C belongs to the range of H. If H is invertible, of course C is going to belong to the range of H, right, because the range of H is everything. Then we had this solution, right? Explicit solution. Everyone remember we did this calculation? So now, when I'm looking at this, what is the explicit formula for my V star? I'm now minimizing this function here. Is this an unconstrained quadratic? Assume your Hessian is positive definite, right? If your Hessian is positive definite, then V star is minus gradient square f of x naught times, what is your C vector now? Right? That is the step you want to take. If you're at x naught, you want to perturb it to go to the minimum of the quadratic approximation at x naught, which is given by exactly this, by the calculation we did in the QP lecture. Okay? So this tells me that I want to choose x1 is equal to x naught minus Hessian square f of x naught times the gradient of x naught. If in general, if I want to do a rinse and repeat on this, I get xk is equal to x, or let's say xk plus 1 is equal to xk Question? Oh, did I forget to write inverse? Yes, this should be inverse. Thank you. Thank you. Inverse. Right? H inverse, Hessian inverse. Sorry, I just forgot to write the inverse part. Yes, question?
How do we make sure the conditions are met?
How do we make sure the conditions are met in the sense that how do we know that the Hessian is invertible?
And also like see like the gradient and range.
So if I have an invertible matrix, then every vector is in its range, right?
Yeah.
So if the one thing I have to check always is that I need to make sure that the Hessian is always invertible. Newton's method only works when you have invertible Hessians. If you have singular Hessians, there's a thing called a quasi-Newton method that you can implement where you basically try to avoid the null space and still find a solution. More involved. We're not going to talk about it this time. But Boyd's book has a description if you're interested. Yes?
Like how do we know that H is PD? So do we require the original function to be convex?
How do we know that H is positive definite? Well, you can actually look, every time you will get an explicit matrix, right?
Yeah.
And you can check it. And in general, if you're looking at a convex function, then you know that's going to be the case.
But what if like this is not PD?
If it's not PD, then you're not going to use Newton's method. Yes?
Is it always true that gradient lies in the span of the column space of the Hessian matrix?
Is it always true that the gradient lies in the column space of... So remember, if I have a matrix A, and A is invertible, okay? What does that mean? Is there a solution to AX equal to B? Right? So by assuming that your Hessian is positive definite, you're assuming that it is invertible. If it is invertible, every vector, and Hessian is always square, right? The gradient is n-dimensional, the Hessian is n by n, so everything is always going to be in its range. Right? There is no null space. Yes? Why would you do this instead of gradient descent? Wonderful question. So, now, if I had a quadratic function, Newton's method will converge in one step. Right? What is the best approximation to a quadratic? What is the best quadratic approximation to a quadratic?
Itself.
A quadratic, right? So you have a homework problem that will show you exactly this. Okay? So you know that basically you're always going to be able, so by using second order characteristics, you can converge much, much faster. Okay? So that's kind of the big advantage of using Newton's method, and that's one of the reasons that it is often used. However, there are multiple downsides to using something like Newton's method. For example, in general, you have to do now an H inverse, right? This is an n by n matrix inverse. As soon as you have matrix inverses, things like your condition numbers start to come into play, right? You now have unstableness, noise, numerical precision issues start to matter. And so for very large problems, you can get much more errors creeping into your problems, right? So numerical instability really starts to matter. Bad conditioning can happen. And so in general, like Newton's method is not necessarily the most popular thing to use. So there's like a pro and a con. You might have remembered a Newton's method from your calculus class for finding roots of polynomials. Does that like ring a bell? This is exactly the same thing. Okay? Why is this exactly the same thing? So another way to think about this thing is to think about what I want to do is I want to say, look, I want to find a v such that the gradient of x plus v is equal to 0, right? So I'm saying that I'm currently at x. I want to take a step to find the point where the gradient is 0. Okay, I'm a convex function. Right? That's a reasonable thing to want to do. But if now I just say that, hey, I don't really know how to do this gradient, can I just linearize this optimality condition? Well, if I was to linearize this optimality condition, what do I get? That linearization is just, so now my function is the gradient, right? So it's this plus right? So if you can think of this as finding a root of an equation, and I linearize it, which is what the Newton's method that you have done in your calculus class does. You're trying to find a root, and then you say, let's pretend it's linear, and find that 0, and then you iterate, right? Remember, you drew pictures like this, like something like this, and then you draw a tangent, and then you see here, then you draw a tangent, then you see here. Remember seeing pictures like this? That's what you're doing, right? You're linearizing, and then evaluating the function there, and then you're linearizing and evaluating the function there. So now, instead of trying to minimize your function, you're saying, let me try to minimize. I'm trying to find the place where my gradient is 0. So let me linearize my gradient, pretend it's a linear approximation, and find the point where it's 0 and iterate. Okay? So that's how it's used in the context of finding roots of polynomials. It's no different. It's exactly the same thing. Okay? So with that, we're out of time, I think. I will see you next week.